please feel free to unmute and then, make your contribution.
Hello.
Yes, hello, Adams.
Yes, sir. Good afternoon, sir, and good afternoon to everyone. Yes. My name is Adams from Executive Director SASNet. Unfortunately, I missed the two sections
And so that's the essence of the school. So if you go to the GitHub repo, which I believe I'm already sharing, but I'm still going to share the link with you from here. So if you click on the GitHub repo, you should be met with this interface. There's a 2023 school with the onboarding, and then there's that of webinar day 3. So just as we've been doing all the time, so with a PC or even a phone, you are still good to go. Just go to a new browser, just type in Google Colab. So we just Google search Google Colab. And then once we have this, we click on the notebook. And then like we explained in the previous times, we said this has to be linked to your Gmail. So if you are logging in the first time, it would request an authentication, and then you'd have to log into your Gmail for it to be seen. Now, since we are loading or opening our notebook from the GitHub, we would have to click on the GitHub so that then we'll request the URL. And so the URL that we have in the chat, which is the GitHub link, we paste that right here. And you can click anywhere outside it. So once we do that, we would have access to the notebooks that are loaded. So if you look into the GitHub, we have these 2 notebooks, and that's clearly what is seen here. And we'll be working with that of day 3. I believe this part is, well understood. So once you have this, you just click on the onboarding webinar day 3, and then it opens in the same terminal, or you can just click on the pop-out over here so that it opens in a new tab. And that's it. And there's the notebook we'll be working with today. So as much as possible, if you have it, just let me know. So I'm just going to allow some 2 minutes so that we are all able to get access to the notebooks, and then we follow through. So that if there are any questions, you can just ask. So, but if there's something you don't understand so far about the procedure, or if you want me to take it again, just draw my attention. Let's do that.
Hello, sir.
Yes, hello, Adams.
Could you please go over the procedure again? I think there was breaks, drop off, the network wasn't stable.
Okay. All right, so the first thing is there's the URL for the GitHub. Okay. So we would have to copy that URL, and then just open any new tab and just do a Google search, or any of the search engines. You just search for the Google Colab. All right, so either you are using Microsoft Bing or you are using Opera Mini, Edge, in any of the search engines. Just type in Google Colab, as in collaboratory. So Google Colab. And then we have these prompts. Now we are interested in the notebook because we are going to work with the notebooks. So we click on the notebook, and then I said earlier that this is a product of Google, so it has to be linked to your Gmail. So if you've not logged into your Gmail account, or this is the very first time you are logging in, it would present you with a prompt that would then request your login, and you'd have to then, log into your Gmail, and then it will bring you to this point. Now, when you're here, you have the option of loading the notebook from different locations. Your Google Drive, if you have the notebook there, you can load it from there. And if you have it from your desktop, you can even upload it. But since we are loading this from our GitHub repo, that's the summer schools GitHub, that's the school's GitHub, we just click on the GitHub, and then up here, we would paste the URL we copied. And once you click it there, or you paste it there, you can click on the lens over here, which is the search, or you click anywhere outside. Then what it does is to go to your GitHub, it goes to the GitHub repo, and then it would pull all the notebooks that it found out from there and would present you with that. So we have that of day 2, which was yesterday's notebook. And we have that of day 3, which is today's notebook. I said, once you are here, you just click on the notebook of interest, and then it would open that particular notebook for you. And that's what we've done so far up to this point. So as many as have any issue, you just draw my attention.
Okay, thank you.
Okay. All right. Okay, so we probably will spare just a minute for everybody to get to it, and then we can then continue. All right, so I'm guessing we are all okay at this point. So now with this, all we'd have to do is be going through the process. And I said each line of code is a cell, okay? Each of these lines, they are all cells. And so for instance, if I go to a cell that has, let me just go down to a cell that has a code. Okay, all right. So just a minute, I think I just need to upload some files to the GitHub. So kindly spare me just a minute so you can see the files properly. So please just a minute, I'm just uploading some items to the GitHub so we are able to follow through. Cells. When we talk of the cells, let me use any of these. For instance, this is a cell. Now, it's either a code or it's in the form of a text from the Google Colab. If you are using the Jupyter Notebook, you would have a code, you would have, or a markdown. So I have the two open. There's the Colab. Just close this. So I have just one. So there's the Colab. And then the one on the very far left is that of the Jupyter Notebook. So if you look up here, we have code, markdown, and then some NB convert, and then heading, right? Now, the codes are the ones that would be interpreted as lines of code. They would be executed, they will play an action, they would give you an output and all that. The markdown and the rest are treated as text. So you can do any sort of formatting. For instance, all these information we are having here, you are able to format them out. And these are purely because they are either markdowns or they are any of the NB converts. And think of it as just the way you probably work in the notebooks. I mean, when we're in, basic school, you have people using like all these red pen and blue pen things, and then just, styling their notebooks so that it's more ordered and more structured. And that's typically the same thing. So you might have some that are codes, which would produce outputs like this one. And if you want to see the ones that will produce outputs that are codes, you would always see that there's an in and then a square bracket. All right, meaning when we run this, it would be executed as an input at a particular instance, and then it will produce an output. And then the ones that do not have the in and out, those are the text formats. All right, so just so we understand that in this instance, everything we'll be working with will be cells. So if you want to run any of the cells, there are multiple ways you can do that. So I'm just going to be going back and forth on this. So if I want to run any of these cells, you can just hit the play button over here and it will run the cell. Or you just go up here to the runtime, and then you can click on run the selection and it will run that selection. If you want to run all the selections, you just click run all and it will run all the script for you. All right, so I think on this premise, we can then start. So we said we are working with NetCDF data. Now, yesterday we had a look at tabular data, and I said that tabular data is mostly just two-dimensional. It has just rows and columns. So a typical example is you take the Excel workbook and you have rows and columns, all right? So any data that's structured in that format is just a 2D data, and that is just a tabular data. But then you might notice that now data capacities are getting bigger, and you can't store all these huge data sets in just a normal Excel sheet. And so there are other formats that are coming up to store the data. And of course, data doesn't vary just in 2 dimensions. You can have data varying in multiple dimensions. So imagine we have data of air quality all over the earth, all right? And it's for each point of the earth. Even if we take just the major cities alone, that's a huge region. And then if we now decide to add, let's say there are vertical levels to it, then it means we are increasing the dimensions of the data. And it becomes very complex to store in just a normal CSV file, right? And that's where the essence of the other multi-dimensional data sets or the data structures come in. And one of the examples is the NetCDF. Now, NetCDF is actually very useful. It's actually known as a network common data form, and it has a lot of functionalities. So it is self-describing. That means the data has the data in it, and then it also has a metadata. And metadata is just like information or background information to the data itself. Now it's also portable. So you can see huge data put into just a small file size and then just easily, transported with, say, a pen drive or even sent via the net. It's also scalable, means you can cut them into chunks. You can split into particular, maybe regions of interest to you. And it's appendable, means you can add new data to the existing one. So even though it's a bigger data, if you want to expand it again, you can still add onto it. And that's what makes it very useful. It's also shareable. You can share onto different platforms, not just, say, working on, say, a Windows platform. You can even share to somebody working on, say, a Linux interface, a Mac interface, and would still be able to work and achieve something. Then it's also archivable. That means you can have huge chunks of data sort of easily archived. And this, what I was saying about the large span of data. So you might have data, which is, let's say, for a point location, but it also varies in, say, a particular other dimension, which could be, say, time. So let's say we have this particular region with a point having information, and then that same point information has been retrieved over different dates. So let's say from 22nd December 2001 at midnight, all the way throughout the day till the next midnight, right? And that is already a large span. It's already 3D because you've got longitude, latitude, and you've got time component. And so there's just a description of how the data format will look like. And so in order to handle this data, that's where Python is also a very effective tool. There are various languages you can use. But in Python, which I explained from yesterday, you have what we call the recipes or the modules. So if you are going to the kitchen to cook, you don't need to know from scratch. You just go with a recipe, look at it. Okay, it says add this, you do that, add this, you do that, and you get your result. So it's the same. If you want to work with the net CDF data, you would have to use any of the recipes. And so there are various recipes. There's the net CDF4, and there's also XRE, and there are even more net CDF reading packages. So we'll be focusing on the XRE. And so, for instance, I have this huge data, which contains temperature information, it contains precipitation information, it has longitude and latitude information. And then we can see that the dimensions are, variable. So we have this data varying in, say, longitude, let's say longitude, latitude, and then say time, all right? That's already 3D. And so we would then need to understand that XRE will be able to read this data and then read them across their dimensions, across their respective coordinates, and then containing also the variables themselves. And that's the usefulness of the XRE. All right. So we will be using just a sample data. So like I said yesterday, we will need to import some packages. Now, the data is contained in the GitHub repo, but unlike the CSV that, of course, we're able to just call easily because of the size, they're slightly larger. And so GitHub wouldn't allow us just to use the, open CSV approach and then just call it. So we need to import requests. Okay. So we import requests, and then we'll now specify from here, this where the file is. The file is contained in our GitHub repo, and it's called rainfall.nc. So we specify the URL, which is where it's going to copy the data from. So if you look up here in the data, there is rainfall.nc. Okay, so if I should open this one up, now there's the location where we are going to put the data. So the raw format is what we would be able to sort of copy, all right? But I noticed that this wouldn't allow us just to show the link and copy it. But at least based on what we did yesterday, we have the file, so we can equally just do the same copying from here and then go into our notebook and paste the URL or the link. And then we also define a local file where we want the file after its download to be stored, all right? And so we just using the same name, we are calling it, say, rainfall_data.nc. That means we'll pull the data from here and write it into a new file called rainfall data in this Google Colab environment. And then we've just got some helper functions here that's just going to help us pull the data. And so once we run this, it will take a little while, but then the data gets loaded. And so now if we check into our directory, we should have rainfall_data.nc. And there's the data we just downloaded onto this place just to be able to use. Okay. Now, in order to make use of XRE, we need to import it. All right. So the main line we need is the XRE. So once we run this, we'll have XRE imported. Now, the other lines of code are in there. They are only, sometimes you run a set of code and then it would give you a prompt. It's not necessarily an error. It's just a warning telling you that, okay, this thing has the chance of being obsolete in some time to come. All right. So if you don't want your page to be flooded with all these warnings, which are not errors, you can just ignore them by importing the filter warnings from warnings, and then you just ignore. All right. That's why we have that here. But the most important part is we are importing our XRE as XR. Now, after importing XRE as XR, we read our data, which is in the local file name. Bear in mind, we assign the file name to this variable local file name. So if I call local file name, it's going to pull this data set. All right, so in XRE, there's the open data set child. And I explained from yesterday that whenever you call the parent package and you need a child package, it's just the parent dot the child. So we imported the parents package, which is XRE as XR. That means whenever we call XR, we are referring to XRE. So from this XRE, we now call the child package, which is the open data set. And then what data are we reading? We are reading the data which we've stored as the local file name. and then we just assign it to a variable called DS. So that means after reading this data, everything is assigned to DS. So if we check DS, we'll see what is contained in that particular file. And that's our data. And so we've read the data set, which is the netcdf format data, and we can see it has time dimension, and on the time there are a total of 60,265 elements. There are also bounds, which we can actually skip for now. There's the latitude, which contains 12 latitudes. There are longitudes, which contains 6 longitudes. All right. Now, these are just the dimensions telling us the orientations of the data. That is totally different from the coordinates. Now, when you come to the coordinates, you see that we have the dimensions stated. So there's a time dimension, but this time there are also the content of the dimension. So it tells us that the dimension contains date-time format, and then these are the values in there. So if you click on this cylinder, you would see that the values are specified. And that's the difference between the dimensions and the coordinates. The dimensions are just telling us how the data is going to be distributed, or in which particular directions they are going to be distributed. But the coordinates are clearly the values that are sort of identifying the exact locations. So if you remember from high school, you have like, okay, A21, and you're told to plot a marker at A21. And you first pick your 2 and you say, okay, on the X dimension, that's 2. On the Y dimension, that's 1, right? The X and the Y are just the dimensions, just showing you the directions. But then the 2 and the 1, which is the value, tells us the exact coordinate. That's why you then, after plotting your marker, you specify A into bracket 2, 1, which is the coordinate. All right, and that's typically the same thing here. So for each dimension, we have associated values, and that's what makes these ones the coordinates. And then there's also, the main thing we put is just treated as a data set. So there's a data set, and it contains variables. All right, so there's a time bounds, the latitude bounds, longitude bounds, and then our precipitation, which is the PR. And then there are also some indexes, and then some attributes, okay? And of course, these are just telling you some background information. So you remember from the top, we said the netcdf contains the data and also contains information of the data. So it's self-describing, it has attributes. So without even knowing the data, you can see here and then know, okay, these data sets were from what? Some simulations of the recent past, right? And they are from CMIP 6 and so on and so forth. And you can tell where it was made from, who contributed to it, and so on and so forth. Okay. So now we've called our data set as DS. And so we then can look at some background information, some basic information. So if I need the information, just as we saw at first, just the ds.info. And then with my parentheses, this will tell us the information, all the attributes and so on, and then every other thing we need to know. Now, if I'm only interested in the attributes, my ds.attrs, which is the attributes, should give me the attributes. All right, so it tells us what the attributes of the data are. And then if I'm interested in the dimensions, ds.dims will give us the dimensions, okay, which is telling us these are the dimensions and these are the total number of elements for each dimension. And then now if we want the coordinates, that's not just the dimension, but the elements contained on those dimensions, that's it. It tells us ds.coords would be for the coordinates, okay. And then if we are now interested in the data variables, ds.data_vars should just give us the variables and tells us, okay, these are the variables we have. Now, if you want to close the data set, of course, the ds we had .close, and you close your data set, but we don't want to close it now since we are still going to work with that data set. Okay. All right, so now from there, once we know there are variables in the data, we can then select the variables. So we have another look at our data sets, and we can see these are the variables in there. And yesterday, when we looked at the pandas in the final sessions, we said there are 2 ways you can select columns from pandas using the dot approach or the square bracket approach. And it's the same. XArray is built upon the pandas. So if I'm calling a variable, I call first the data set and then dot the variable. Now, once I'm using the dot, I don't need to call this as a string. I just call it the way it is, .pr. But if I'm using the square bracket approach, it means my ds square brackets, and then I'll need to call the PR here as a string. That means in single or double quotes. And these two are all ways of calling your variables from the data set. So you can give it a try with the lat bounds and then the time bounds or any of the other ones. Okay. And this gives us just the output we need. But then we can see clearly from here that, in fact, let me even throw it as a question. Yes, so there's a question. It says between ds and then the ds.pr, what do we see as a difference? So for instance, when we did ds.pr, this is what we had. Okay. And then when we did ds, we typed in ds, this is what we had. The very first point of difference you can see is that up here, this is the ds is named as an xarray.dataset. And then over here, there's an xarray.data-array. And then right by this, we do not see anything, but by this one, we see the variable has been called before the dimensions show up. And that's clearly because the second option is a data array. Whenever you call just one variable from the whole data set, you're now dealing with a data array. So just as yesterday, we saw data frame and then series, and we said a data frame is a combination of series. So when I take the entire Excel book, every column is an individual series. When I put all of them together and we have a complete row by column, we have a data frame. The same way in Xarray, when we pick any individual variable, that's a data array. When we merge all of them together, we are getting a data set. So a data set is a combination of multiple variables or multiple data arrays. All right. And so we can just quickly check the type from here. So like we did yesterday, once we call the type, we're trying to see the data type. And so we want to see the type of DS. And it tells us that this is a data set produced from Xarray. And then the second one, which is a ds.pr, is a data array produced from Xarray. And then, of course, this is the same as just having ds and then the square bracket approach instead of the dot. And we put the PR into strings. And we get the same output. Okay. And so we have some background information here to help you understand the difference between data array and then data sets. Okay. All right. And while I'm going on, if there are any questions at any point, do not hesitate to stop me and then ask, or you can also type it in the chat. And so just as we did for the data set, we can also check the same attributes and then other, features of the data array. So ds.pr, which is our data array, we can also check the attributes by saying .attrs, and this gives us just the attributes. And these attributes are only limited to only the precipitation variable. So you see, it tells us what the standard name is, what the long name is, which comments are included, what the units are, and so on. Now, this data has been changed, so the unit you're having here wouldn't be the same. So we would have to find a way to replace that name. And so we would see how to do all those ones way easier. And so if I'm interested in, say, the standard name, once I have ds.pr.attrs, I can bring my square bracket, which is just to subset or call something out. So now I'm going to call the standard name. So I just call this standard name by copying this standard name in a string and passing it into the square bracket. That means go into the ds.pr data array and then select the attribute, which is standard name. And then that's it. And it gives us just the standard name attributes. Okay. All right. And so that's what we have in the next cell, which is what we just tried out. And then we are saying that if this is probably wrong and want to change it, it means we can reassign. So just as we are able to call this, now the unit here has the name units. So if I'm interested in that part, I just change the standard name to units. And this gives me just the units. And we are saying that this unit is wrong. So the unit actually should be in meters. So I can just add an equal sign and then bring my M as a string. Yeah. And then what this means is that we are assigning the value M to the variable, which is the units. And we explained it from yesterday that whenever you have variable assignment, the left-hand side is a variable, the right-hand side is the value. So once we run this, it's going to change the units from the kilogram per meter squared per second to just meter. So we do that here, and then we can check the attributes of the units again, and that is it, that's changed. Now within the data array, we can also check the shape. So we have our data array dot shape. This gives us the shape of the data. That's 3-dimensional. And then these are the total elements on each dimension. That represents the shape. Now, if I want the size, that's the product of all these. So the size of the data is this. So we have these number of data points. That's what this means. And I already explained the difference between coordinates and dimensions. So I don't think we would have to take it again, but we can just simply look at the outputs of the dimensions and then the coordinates. And that's it. Okay. Now, the next thing we want to do is just to select the data or subset the data. So to make this easier, I'm just going to assign this whole dataset.pr to a data array, which is DA. So a new variable name, that's DA. It means when we call DA, DA is referring to just the precipitation variable of our data set. Now, if I'm interested in selecting just a particular time, now look here, we have different time steps. And it starts from, say, 1850 all the way to 2014. Okay, and this is just sample data just for test, all right? Now, this is a daily data because it starts from January 1 at midday, then it goes to January 2 at midday. So if I'm interested in, say, 1850, January 2 data, all I need to do is from this DA, let's add a new cell down here. Okay, so a code line here. So all we are doing is that from this DA, we want to select, so DA.cell, all right? And what are we selecting? We are selecting from the coordinates of what? Time, or from the dimension of time. So we have to specify the dimension here. So DA.cell, and in fact, when you get confused and you don't know what to do, you can just hit your Shift and Tab, and it will give you a whole lot of options on how this works. So DA.cell, and then we specify the dimension time, and then we are interested in 1850. All right, now you notice that these are in single quotes. So it means even though they are time, they are treated as strings. So we have to do the same thing. So we have the strings and then 1850, January 1. Now with this, we are able to select the data for just January 1. And then you can see that the time has reduced. So unlike the first one where we had different times, now we have just the time for the first January 1850. And that's how to select the data. Right, so you have the data array.cell, and then you specify the dimension, and then select the value that exists within the values you have. But there could be instances where you are trying to select something and then it doesn't exist in the data. That's where you have to use some interpolation of a sort. So, okay, we can skip this. And then once we've selected the data, so for instance, in this case, we are using 2014 1st June, all right, and assign it to this variable. Now we can easily just see what it contains by calling the variable we've assigned it to, and then say dot plot, and then open and close the brackets, and then we would have just a time series. Okay, sure. No, there's actually a spatial plot because we selected for a particular time. Yeah, so yeah, exactly. So we have longitudes and then latitudes still conserved. So this is just going to give us a 2D representing the spatial data for this particular day. All right, and that's what we have over here. Now, similarly, if I just say I select my ds.pr, which is the data array, or which we can replace with DA in this case, I select that for all the month of June 2014. Now, you notice from here that once we select for June 2014, it's going to bring out all the data sets for June 2014. Sorry, I didn't need the mean over here. So just selecting for June 2014, you go down here and then you click on the cylinder. You see that contains all the data from from 1st June 2014 all the way to 30th June 2014. Now, if I'm interested in finding the mean of all of them, it's easy to apply the statistics to this because once I select, it gives me all of them. And then I can just find the mean, say dot mean. And I need to specify over which dimension. So that doesn't give me just one value for the whole thing. So I am interested in the dimension of the time. So I would pass here time as a string so that it gives the time average, all right, for that particular period. And so we'll have the time average for each grade. and that's the output. So it's very easy to sort of do your manipulations or visualizations and other analysis with the XRE using the NetCDF data. And then, of course, once we are done, we can again visualize this, which will give us the mean information for, that's the average rainfall variable for June 2014 for this particular model. All right. Now, similarly, you can just select by, say, longitude. Now, these are the longitude values. So DA.longitude will tell us the longitude values we are having. Now, if I'm interested in just, say, the first longitude, that's longitude negative 4.6875. So with this one copied, I just go down here and then have DA.cell. And then I say, okay, which dimension do I want to select from? I want to select from the longitude. And then which longitude? That's the value negative 4.6875. All right, so once I do this, this value is recorded within the longitude. So it would know exactly where I'm selecting, and then it will go back there and then pull the data. But if these points were not existent, let's assume I have, say, 4.695. I hope this doesn't exist somewhere. Yeah. Now, because this point, this value is not existent, it's non-existent in this these array elements we are having, it produces an error. So if I'm using the cell method, then it means the value I'm calling should be in there. But then there's also the other alternative where you can use the iCell. iCell means just index selection. So if I'm not certain of the value and I just want the first position longitude, so this is position 0, which we said Python starts from index 0. Then I can just make use of the iCell. And once I use iCell, I'll be selecting by their position. So it means the element negative 4.6875 is on position 0. So if I do this, then I'll get my output, which is the same as selecting with the cell and calling the value itself. So all these two are different ways by which you can handle your data sets. All right. And then now we want to select data for a point location. So you have, like, let's say we are selecting for Kumasi, all right? And there's the latitude, there's the longitude. And of course, we know these longitude values and latitude values we are seeing are not existent in the latitude and longitudes we showed at first. So how do we do that? So, of course, if I need some help on this, just help on the dataset.cell will give me a whole documentation. But then what we want to do is now, because the location doesn't exist within our latitude and longitudes, we can then make use of an interpolation. And there are different interpolation schemes we can use. One of them is the nearest neighbor. That means if I do not find data for this particular location, then I should look for the closest location that has data and then use that data as representation of where I'm interested in. So for instance, we select and we specify that on this longitude, we are interested in negative 1.624, which is what we have here. And then also for the latitude, we are interested in the point 6.6885. And since we are not certain whether these 2 points exist, we just apply a method. That's the interpolation method. And we tell it, okay, use the nearest neighbor method. And so this will pick the closest point to it. So if you look down here, even though we specified negative 1.624 as our longitude, we come to the longitude and the value is rather negative 0.9375, meaning this is the closest point to the longitude we specified. And then 6.6885, we rather have 6.875, which is the closest latitude to the one we specified. And that's how the nearest neighbor works. There's also the forward filling. So it will just sort of create a pattern. So it picks the closest data and then moves it to, it picks the one that's directly ahead of it and uses that to fill the data, irrespective of how close it is or how far it is. So it depends on what you are trying to achieve with any of the interpolation methods. And that's just the point selection. Yes, Eric, you have a question. Please go ahead.
Yeah, okay, so say, I would like to ask, can you use the method nearest at where you use the iCell, the A.iCell? When you use, you're trying to select only one longitude without adding the latitude to it. Can you use the method nearest also there when you are dealing with only one, let's say, dimension, that is the longitude or the latitude instead of the iCell?
You see, the beauty, I get a question. The beauty of programming is everything is testable. You can test it out and see. But if you are selecting by positions, you just you don't even need to know the value. All you need is just the position. So for instance, I do position 1, I specify 1. Okay, that's what you are interested in. You get it. So you can give it a try and see, but then typically, I mean, that's the essence of programming, to be able to experiment. Okay.
Jeff, I just wanted to add that
Yes, please go on, Edmund.
Yeah, I just wanted to add that like with the I cells, for example, those ones, like, it's common with positions. Yeah, and then so if you want so if you want like positions, it's better to go with the I cell. But then the last one that you were demonstrating with the nearest, once you want to select like data, you will need, because those data are geolocated with longitude and latitude. So once they are geolocated with longitude and latitude, you will need any of those methods, like the nearest or any of their methods, to select the longitude that is closest. Sometimes you might not know the exact, or maybe the values that you are going to give might not give you the exact, like it will not be the same long lat as coded in the data. So these methods are okay for you to help you get the longitude or the latitude that is closest to what you are inputting. And that's why you will need those, the method, for example.
That's true. And then even the interpolation. So you see, nearest neighbor is where it picks the closest point. But there are different interpolation techniques. So you've got some interpolation that would rather do an average and pick the points. They'll try to establish a pattern and then smoothing it. So it might not be necessarily a data from a neighboring station, but it looks at the trend between, let's say, the station before you, the station ahead of you. And then based on the pattern, it says, okay, if this is 6, this is 4, and you're in the middle, then of course yours will be around 5. Okay, so all these are like smoothing approaches. All right, so you decide or you determine what you want to use based on what you want to do. All right, and then we also have the aerial slicing or aerial selection. So if I want to select for a particular range of area, the same cell approach, but this time I specify that the longitude should be a range. All right, so I'm interested in the longitude of -2 and 1. Okay, so it would fix a lower limit at -2 of longitude and then 1 as maximum for the longitude. And then any point that falls within these two ranges will be selected. And then the same for the latitude. So ranges of 5 to 7.5 would be selected. So the intersection of these 2 points are just the data sets that will be selected. Now in this approach, you don't need any method because slicing is just over sort of a huge box, right? And of course, once you have our data selected, we can just do a quick visualization. So one thing you need to understand is that whenever your data is one-dimensional, by default, it's going to produce a line plot. When it is two-dimensional, you have a spatial plot, or well, you can term as a contour. And then once it's three-dimensional or it's more than three-dimensional, then you are going to have a histogram, right? And so let's try an example. So we select, say, that of June 2014. Now you look here, we have 30 points on the time, 12 points on the latitude, 6 points on the longitude. Now there's already three-dimensional, containing different elements, okay? So now let's try and plot the same data. This is three-dimensional, so we expect a histogram. That's it. And then let's go on to select a particular day, say 15th of this June. Now this is going to be a two-dimensional because we are selecting just one time step. So this is equally there, that's not even known, but rather what varies are the latitudes and then the longitude. So once we plot this, we are going to get a two-dimensional plot, which is a spatial plot. Okay, and that's it. You can see we have the latitude and the longitude shown, and then the parameters we need. And then if we are selecting our point location, because once we select our point location, meaning a fixed longitude, a fixed latitude, the only thing that varies is our time. So it means this is a one-dimensional. So once we plot this one-dimensional, we're going to have a line plot. Okay, and those are like the defaults. Okay, so whenever it's one-dimensional, line plot, two-dimensional, spatial, more than that, you have histogram. And then we can also group the data because the data has a time component. And of course, you can do the grouping not just over time, you can do it over any of the dimensions. But since there's time, we can equally do the groupings way, way easy. So I pick my data array, and then I group them by, say, the years. So I have a group by, and then I specify that on the time dimension, I'm interested in that of the year. So let's try something out here first. So maybe that will give some clarity. So for instance, I have my data array, okay? And then I'm interested in the time dimension. So da.time will give me just the time, all right? And you can see that clearly from the time, there's a year component, there's a month, there's a day, the hour, minute, and so on. And this is regarded as a date time, all right? So of course, if I'm interested in selecting any of these, now, the best is to use the square bracket approach. So in that case, my time would then be as a string, right? Which is still producing the same thing. But if I'm interested in the year, now time.year would give us only the year component of the time. So you can see clearly all these time steps have just been reduced to their years alone. So you have like 1850, 1850, and so on. No month, no day. If I'm interested in the month, time.month, and it will just produce only the months. All right. And that's it. So once we have that out of the way, it means we can also perform the grouping. So when I'm creating a group by, all I'm trying to say is that, for instance, I'm interested in the year. So let's make use of the time.year. The groupings are just going to create containers. So we have a container that will store all the data for 1850. All right. It's not going to do anything to it. It's only going to store the data into a container that's for only 1850. All right. So let's say we have this DA and then our group by. And we are telling it to group this on time.year. Now it tells us that it's created a grouping and we have a total of 165 groups. And each group has been labeled. So there's a label for that of 1850, there's a label for 1851, 1852, and so on. So in 1850, we have all the data sets that are contained in 1850. And there will be no data from any other year. In 1851, you have data from only 1851. Now, if I'm interested in doing something to it, let's say I want to find the mean over them, then I can perform the mean. And then this would go into the respective groupings and then find the mean of every group, all right? And this would now give us the, yearly means. It's taking quite some time. Yeah, so now you can see that the time component has changed to what? Year, telling us we only have 165 years, all right? So this will just produce the mean now over the containers. And the containers were yearly containers, so it will give us the yearly means, all right? And you can equally just perform the yearly sum. And if you want, you can specify that, okay, you should do this over the time. I mean, it's still the same thing. So we have A1 being the annual totals. And so that'll be the total for every year. And so if our A1 contains the respective years, then it means the variable dimension, which was time, that changed to year. On this year, now there are different year values. And bear in mind, these are now integers, not strings. So I can call any of the years and then plot it. Let's say I'm interested in 2014. So I say A1.cell, and I specify the dimension year to be 2014. Now, when I do this, it's going to pull out only the 2014 data. All right. It pulls out just the 2014 data. So you notice that the year is only 2014. And of course, now it's two-dimensional, so you can visualize it. Okay. And you see what's happening for that particular year. Now we can also find over the A1, which is the year, month, the year, longitude, and latitude, we can find the mean over, the areal mean, that's like the area average, that's over the longitude and latitude, and we'll be left with only the years. So once we have this done, you see that the longitude and latitude have been averaged, and then we have just the years. Okay, so the values have been averaged over the longitude and latitudes, and we are left with just a time series. Now, if we plot this, we would only see the yearly, the areal average of the yearly totals. Okay, and this tells us that for the region we are looking at, this is how their yearly totals vary. Of course, bear in mind that these are, some values that have been sort of altered in a way. So, we would have to In fact, if we want to do the conversion properly, then we'll have to do the conversion from the kilogram per meter square per second into proper, either meters or millimeters. All right. So the most important thing should be on the patterns we see for now. Okay, so similarly, we can do same for the months, and this is just going to create 12 bins. Okay, so January's into one. So January from every year would go into that particular one box, and then now we are finding the mean over them. And this is just like the monthly climatology, right? And this gives us just 12 values over the times. Okay, so we look up here and we see the month, and it's just 1 to 12. So of course, we can select any of the months and then visualize what the climatology for that month is. And since there's just quite an easy thing, we can also create a facet plot. So the monthly mean values, we can plot them, and we tell them that, okay, for every 4 row elements in each, for every 4 columns, it should just do a wrapping. So if just like you do with your Word document, okay, if it gets to the end, it has to wrap them. So if the word is not complete, it will just move it to the next line, so on and so forth. All right, so all we are saying is that we are going to make a plot where we are going to use the months as all the, column elements. Now, we have 12 months. So if I start plotting for, say, January, the next panel is February, the next March, and then April. That's already 4. Instead of continuing with the 5th and the 6th, it's gotten to the 4th month. So now we wrap over there, and then we come back to the bottom of the 1 and position the 5, position the 6, the 7, the 8. That's also another 4. And then we just wrap again and go to the next line. And so this is what we call just a facet plot. So that's it. So you have that of January, February, March, April, and then it doesn't continue. Now it wraps this and then comes back. So we said it should be 4 columns in order to wrap. So let's say we now have 6 call wraps. Then it means after 6 columns or 6 entries in the columns, then it will just come to the next row. All right. And that's it. All right. And then just as we have the, the year, the month, we can also, because it's a time series, we can also find the season. So this is just splitting them into the DJF, MAM, SON, JJ seasons. So we group them by time.seasons, and then this will just give us the seasonal information. So you can find the mean, the max, the minimum, all the statistics over the seasons. And you can see the seasons are just DJF, JJ, MAM, SON. That's December, January, February together, June, July, August, March, April, May, September, October, November. And so since they are 4, we can also perform a facet plot, and we say, okay, we need 2 columns per, 2 columns, and then we wrap. And that's it. So in order, and this in alphabetical order. So DGF, JJ, then MAM, SON. That's it. And then aside the group by, we can also do a resampling. Now the resampling is just trying to either downsample your data, or you're trying to upsample it. So it's slightly different from the group by. They perform quite similar rules, but they're slightly different. So in resample, I pick my data array, add a resample, and then I specify that I should resample this on the time component or the time dimension, and it should be every year. So this is just going to say pick the first year, perform a certain function on it, go to the next year, perform a certain function, all right? But it's going to be based on the groupings I give, all right? And it has its own advantage. So with this, we have exactly the same annual means, but this time, the time component or the time dimension doesn't change to year. It is still conserved. The time is still preserved. All right. So if you look down here, this doesn't change to year, still time. All right. And it gives us just the end date of that particular time for each particular year. And the beauty of it is that now with this resample, unlike the group by, when you put them into months, it means it's going to group the month from every year into one cluster. So if I'm interested in January, it's going to be January for all the years. But what if I'm interested in, say, January 2001 as a separate thing, January 2002 as a separate thing? That's where the resample comes in. So by this resample, it means I'm just resampling them by each month, and then I keep the values at the start of the month. So if it's January, it wouldn't pick all Januaries together and group them together. Rather, it will pick, say, January from 1990 as one cluster, group them. go to February 1990 as one cluster till it gets to December. And when we are done, January 1991 as another cluster. So you have the respective month variations per each year. And that's what makes the resample a bit advantageous. Okay. But that also then consumes some time and some memory. Okay. And then while it's running, we can also do this on the quarters. So let's say every quarter. So the QS means the quarter. So like January, February, March is one quarter. Now, the good part of this is you can specify which month it should start from. So I'm interested in starting each quarter from, let's say, January. So it means we'll have January, February, March together, and then April, May, June together. So instead of doing DJF, we're going to have something like JFM as one, then AM into the next. So January, February, March, April, May, June as another one, like that. And then it should be stored at the start of each one. So for January, February, March, when we average them, we'll be storing this at the start of January. That's going to be, say, 1990, January 1 will contain this value. And that's it. And that's what makes the resampling also quite advantageous. Now, this is taking a longer time to load. I hope it comes soon because we have just limited time. Let me stop, let me terminate it. Okay. But you can test it out later on your own and then you see how it works. Okay. And then we also have the where method. So the where method is also another way of trying to, select particular portions of the data and drop other parts. So for instance, I'm interested in, let's say we want to multiply this by, say, 1,000 so that we increase the weight of the values a bit, okay? And then we find the mean over the time. And so we are left with just a 2D when we find the average over the time. And so we can just plot this out to see what the output is, the spatial plot of our 2D. So it means DA to slice is this data we want to slice. Now, what if I'm interested in only values over a certain latitude point? So let's say I'm going to set a latitude at, say, 6, and then I need only the values that are above 6. That's above latitude 6. That's where the where method comes in. So we have this DA to slice, and we say from this whole data, wherever, I think let me just make use of that same thing, even though the DA will still work. This will make it easier. So from this whole DA to slice, wherever the same DA to slice, its latitude is greater than 6, that's what we want. So by doing this, in fact, let's go back to this. So when we look at our DA to slice, we have values everywhere. But the moment we bring the where method, some of the values will change to none. Those are the ones that do not satisfy the conditions. So the ones that do not meet this criteria will be changed to none. Those are missing data. And then when we plot, you notice that we have data for only the parts that we are interested in. That's the ones above 6. All those below 6 changes into none, which is missing data. So the where method has this functionality. You can use that to subset your data. And of course, all these things we are doing, we are saying they are georeference data, but then how do we show them on a map? That's where the Catopy comes in. In fact, initially you had base map, which was working, but now there's Catopy, which is also way simpler to use. There are other forms. There's the GeoPandas, Rasterio, a whole lot of other georeferenced, geographical packages. So we are going to focus on the Catopy. Now to install Catopy, just take this hash sign up and you have this, the exclamation sign, the conda install, and then the Catopy. Now I don't need to install this because in most cases, by default, the Google Colab already has Catopy installed. Okay. But what we are going to do is we are going to import certain packages from the Catopy. So we've seen the first instance of import where we have import numpy, say NP. Now in this case, we are going to say that from this bigger package, which is from the parent, or let's say from this whole household, which is the Catopy, we are only interested in particular elements, right? So think of it as, say, from Ghana, we are only interested in calling one individual. Okay, or we are interested in calling one institution. That's it. So from the whole Catopy, we are importing just CRS, and then we are also importing just feature. All right. And then we made use of our matplotlib.pyplot, which is just for visualizations. And so this is just the easy way to call it. Okay, I think I have to run the installation here. All right. So if you have an error like this, then it means the Catopy isn't installed. I hope it takes, okay. So I'm just going to switch from here to my Jupyter notebook for now, since I already have it installed, so we don't spend too much time. Okay. And then I'm going to run all the earlier codes. Okay. So once that is done, we'll then continue. All right. So I said I have an error somewhere. Let me see. Let's go. So it's purely because I'd already loaded the file. So that's why we had that permission error. Okay. All right, so I'm just running the cells till we get to where we're all at. Okay. I'm gonna skip all these ones and then, yeah. All right, so to our Catupy. So we've imported CRS from Catupy, which is for the projections, and then the feature, which will allow us add certain features. For instance, the country borders and then the rest. And then we imported Matplotlib to help us create a canvas on which we are going to put our plot. So plt.figure means we are creating just a figure canvas. That's like the drawing board where we'll be placing our plots. And we assign that to Fig. Now on this Fig, I'm just going to create sections. So I'm creating smaller areas that I'll just plot. So instead of plotting on the entire, let's say this whole white sheet, instead of plotting on this whole thing, I'm just saying, okay, I'm just going to pick a component of it, just look a particular area of it, right? And now in this whole white sheet, we are saying that we should split the white sheet into 1 row, 2 columns, right? And then we are interested first in the first position, that's the one on the left. Then after selecting this location, now we have to set a projection, which will then make this plot panel be treated as a graphical, as a geographical plot. So we set our projection to CRS dot one of the projections. So in the projections, we have plate carry. For instance, if I go up here, we've imported CRS. So CRS dot, and then I tab, I'll get a list of all the projections and other attributes. And so in here, there's a projection called plate carry, which we are going to use, which allows the Earth to be treated as a rectangle. Okay, so that's what we used over here for the projection. All right. And then once we run this, you would have the rectangular projection shown. Now let's see what the AX contains. The AX, which is the axis we are calling, is now called a georeference axis. So it changes from axis to geo-axis. Now imagine if we didn't have this here, if I close this and comment. Now this is just an axis. It means just a normal plotting axis. But then the projection inclusion changes this from a regular axis into a georeference axis. That means it's something that can be, we can visualize global data, or let's say geographical data on it. And those are just a difference, right? And then once we have that, so we are now going to maintain that same projection. And let me just use a 1 by 1. So meaning just a single panel. So we are using the entire panel. And then all we have to do now is just to add the coastlines. That means we just want to see the continental boundaries. So by adding the coastlines, we would have the continental boundaries showing. Okay, so without doing anything on our plots, we can just see, just by plotting the coastlines, we see all the continental boundaries. And then we want to see, now this is just the plate carry projection. So what if we try a different projection? Would there be any difference? So now we are going to use 2 separate projections, and we are splitting our whole panel into 2. So we have 1 row by 2 columns, position 1. That should be the same plate carry. This should be maintained. And we add our coastlines. And then the one on the right, which is position 2, should be a different projection. Let's use the Robinson projection. And then we call that AX1. And so instead of adding the coastlines to AX, we add the coastlines to AX1. And then we plot this. We can see that these are 2 different projections. All right, so every projection will give you its own layout. And there are reasons for that. It depends on what you want to see, what you want to show. And every projection you give would have a certain level of bias because the Earth is spherical. It's not rectangular. All right. So in order to use a particular projection, there are certain adjustments you would have to do. Now, after adding the coastlines, let's go back to just using our plate carry. We add our coastlines, and then now we want to add a country border. So aside, let's say, the map of Africa, I want to see all the countries like Ghana and the rest. We just pick our axis, which is the AX, and we say add feature. And then from the feature we imported from Catopy, we call that feature, and then we say add, just select the borders, which is the borders subpackage. So feature.borders, and that will just create the country layouts for us. Okay. Now after this, can we just overlay our plot? So we have our projection set for the figure. We've added our coastlines, we've added the borders and the rest. Now I want to add the data. Okay, want to add the data. So let's take this one out first. There's our map. Now we want to add the data to it. And so we picked our data array, found the yearly groupings and found the mean, so the annual means. And then we found the mean of all of them. That's like the climatology of all the annual mean information. And we are plotting that. And we have this keyword AX, which we are setting to the same AX over here, which is, the first one is a variable AX, which is a keyword. The second one is a value AX. That means this AX would be equal to the georeference axis we have over here. And so it's going to plot the data on that same plot for us. And so let's pull these ones out first. And then you have your output. Taking quite some time because of the group by. Yep. Yeah, so that's it. And then it's restricted the whole data and the plot to our region of interest, which is the region we have data for. But what if we want to show the entire region? Okay, that's where the extent comes in. So we have ax.setExtent. And then with the setting extent, we have to set the left longitude, the right longitude, the lower latitude, the upper latitude. So from left, right, bottom, top, right? So by setting this, we then have the extent showing, and this is to cover the entire Africa. So we have the entire Africa showing, and then the data is just over Ghana, and then some neighboring countries. This data is able to plot because we are just using the projection plate carry, and then most of the data sets we have, which are distributed on longitude, latitude, are by default plate carry format. So if I plot the data on this plate carry projection, I would have it showing. But what happens if I use a different projection? So let's say the same plot, but we are changing the projection here from the plate carry to a Robinson, all right? And we just still want to visualize the data. Now, when we generate that plot, we'll see that the projection would show. The map shows, but there's no data, right? We have the map showing, there's no data, but we still have a color bar telling us that there should be some data over there, but there's no data. And you can see that the lines are not even straight, they seem to be curving, all right? Because that's the Robinson projection, right? And so since we want to make use of the data, we want the data to show on this, it means we'll have to sort of convert the projection to conform to the data. And so all we have to do in most cases is that you just have to specify that this data we are using is not in the Robinson format, but rather the data is in a plate carry format, all right? And so this would then tell the data that, okay, you're in a plate carry format, but I'm just going to overlay you on a Robinson format. So then you guys need to be in agreement and then overlay one on the other. And so we make use of the transform keyword. So we have transform here, and then we transform the data and say, okay, we want this transformed into a CRS.plate carry format. That means they should treat it as a plate carry and then try to let it merge with the Robinson format. And then we can then visualize this. So by applying this transform, we then have our data showing. And that's typically how this whole projection works. And there's just, you know, a background information we are given. In fact, there's more things. There are lots of things we'll do during the school itself. There's just a background information. So I would end here. And if there are any questions, we'll take them. Right. So if there are any questions, we'll take them now. All right, so please feel free to ask your questions. You can
They
can
say
ask
they don't have
questions by all
questions.
means.
We'll
that-
pinpoint their names. Let's call by name.